Hello and welcome to Chapter 4. So Chapter 4 is a great chapter which we really start getting into a lot more statistics as opposed to learning about like surveys and different types. We actually start getting into more statistical summaries. So you'll notice in the prior chapter we talked about stem plots and histograms, and we use this to look at the shape, location, spread of a distribution. Now in Chapter 4 we're going to be using numeric summaries for similar purposes. So summary statistics. We're going to talk about central location, or central theorem you might see it called if you look online anywhere. And we're talking about the 3 M's, mean, median, and mode. We'll be going over those, and that's part of the central location. Next thing we're going to be talking about is spread. We kind of touched on this last chapter, but now we're going to be getting into a little bit more. Specifically, we're talking about range and interquartile range. And then we're also going to be talking about the variance and standard deviation. And then we're going to talk a little bit about shape summaries towards the end. So here we have notation. We've talked about this a little bit, but now it's going to be really important to make sure we understand what notations are and what they are explaining. So anytime we see n, it's kind of like an italicized n, it's going to be the sample size that we are dealing with. So if we have an illustrated data of these participants shown here, we would have an n equals 10. So there's 10 participants, or 10 data points in our sample size. Next is x. X is capital X is the variable, i.e. the ages of subjects. So x here would be our age variable. Capital X is our age variable. Next we're going to have x subscript I, which is the value of individual I for variable x. So here we have x sub 1 is equal to 21, right? Because that is the first number we see here. X sub 2 is going to be 42, and so on and so forth, and x sub 10 would be 52. So x sub I is the value of the individual for the variable we are looking at. Next, you'll see capital sigma, right? So we have this fancy capital sigma, which means the sum of all values. You're going to see this expressed throughout all of our equations going through. And anytime you see capital sigma, it just means the sum of all values. So what we'd have here is sigma of x sub I, which is equal to x sub 1 plus x sub 2 all the way to x sub 10, which is 21 plus 42, all the data points to the very end, equaling the sum of 290. So now we're going to talk a little bit more about the mean. And we have the arithmetic average, which is what we just kind of went over, and it's the traditional measure of central location. It's the sum of all the values divided by n, and it's referred to as x bar. So that is typed out when you see it written x bar, and that is for a sample mean. We also what's called mu, and mu is also a sample as well, but it's a sample of a population. We're going to talk about that just now. So here we have x bar is equal to x1 plus x2 to the xnth, however many data points or however big the sample size is, all divided by n, classically seen as the sum of x sub I over n. That is how we find the sample mean. So if you had 10 individuals selected at random to have the following ages, here we're back to our ages again, and we note that n equals 10. Highly recommend anytime we get a data set, first thing you should do is off to the side write n equals whatever it is, n equals 10 here. This will help make sure you don't count weird, and then when you need to know the value n that's already written down, you have to keep recounting the data points. A lot of times it might be given to you in a question. Sometimes you might have to count it up yourself. It just depends, but I highly recommend just getting into the habit of first thing you do is find out how many participants or how big the sample size is, and saying n equals 10 or n equals whatever it is. Then you have the sum of x sub I, which is equal to, like we said, 290. And we'll notice it can be written like this. And then when we write it fully out, we have all the data points, or all the ages here, divided by 10, the number of individuals here, so we have 290 divided by 10 equals 29, therefore x bar equals 29. This is how we would calculate a mean. Add up all the values divided by the total number there. The mean is the balancing point for a distribution, so another way to think about it is the mean is the balance point. The book goes over this and shows this diagram here. If you're a visual learner, this might help you realize the mean is the balancing point of the distribution that you're given. The uses of sample mean. So the sample mean can be used to also predict or to infer about a population mean, right? So we hear that word infer, inferential statistics. It just means that if we have a sample and the observations are drawn at random from a sample, we can use this to predict a population mean. Not always, but majority of the time this is the rule we can follow. When you're calculating population mean, it's very similar to how we calculate x bar. It's mu, here's mu, is equal to x sub 1 plus x sub 2 to the x sub nth over n. You just notice that n is now capitalized, meaning that it's a population. So it's the same operative, but n is the population size. This is conceptually important to see that it's done the same way, just meaning something different instead of just the sample set we're inferring about a population. This is not always available in practice, right? Sometimes we don't know the actual true size of a population. For example, if you have HIV, AIDS, we don't know how many people are actually living with HIV and AIDS currently. We can guess, but we don't know the true population size, right? Much to say, like on any given day, we don't know the actual true population of, the United States, because people die every day and babies are born every day. And so we don't have at a very particular moment the exact amount. We normally can infer and make great guesses, but sometimes we don't have the exact number of population, so it's not always available in practice. We can always sometimes refer to this as the expected value. Anytime you see expected value, we're finding out the mean of this area. Just a heads up, if you ever see expected value, what is the expected value of this data set? We're asking what is the average, what is x bar of this sample set that is given to you. Expected value is going to be what is the average. So next we're going to go to the median, and the median is the value with a depth of n plus 1 over 2. Remember, this is the depth, so it tells you how many spaces in a data set where the median is located. It doesn't tell you what the actual median is. So when n is even, the average of the two values that straddles the depth of n plus 1 over 2, right? We kind of talked about this a little bit in the last chapter. So if we have 10 values listed below and the median has a depth of 10 plus 1 divided by 2, we get 5.5, placing it between 27 and 28. Average, these two values get a median of 27.5. So once again, first thing you have to know is anytime you're finding the median, you have to make sure these are in order. If they're not in order, you can't find the median value. So we take our 10 values and we place them in ascending order, which they are now, and then we have to find the median, it's the middle value. So in order to find the middle value, you have to find how deep into the data set we have to go. So shown here, we have 10 plus 1 divided by 2 is 5.5, so we go 1, 2, 3, 4, 5, 6. So this is 5, this is 6, so 5.5 is right here. This is where the median lies. There is no number right here. Therefore, we have to take the average of the two values that are by it. So 27 plus 28 divided by 2 will give you 27.5, and that is the median value. So here we have some more examples of medians. So if you have this example of a data set containing 2, 4, and 6, the median value here is 4. I'm going to give a little bit of a pause so you can think about it and try to answer, and you have the median here is 4. Example B, you have a data set containing values 2, 4, 6, and 8. The median value here will be 5, right? That's the average of 4 and 6. And then example C, you have values of 6, 2, and 4. Now, if you said 2, that is not correct. Remember, the values have to be ordered first. We have to put these in order. So it would be the same as 2, 4, and 6, and the median would be 4. Make sure you have to put in more. If you don't put in more, you're not going to find the true median value. The median is robust, and what we mean by this is that it's more resistant to skews and outliers than the mean. So if you had a data set, or let me show this data set here, from 1362 to 1868 has a mean of 1600, right? If we take the same data set, but let's say we put in an error, we fat finger one of the values down here. So all these values are the same up until the very last digit, and we fat finger and put something in wrong, right? This could be a common error if you're not paying attention to what you're doing, and if you put it in, it can be very bad. And if you do this, you'll see that your mean of this data set is 2,742.8571. Now, towards the end of this video, I'm going to talk about rounding and the decimals and explain a little bit more about how the rest of the class will go, except you will see sometimes the decimals going out 4. That is something that I've always practiced and have always done, so it's going to be hard for me to break this habit a little bit going forward, but it just means I'm going to be a little bit more precise in my answer than how I want you guys to round and carry significant figures going forward. But as you can see, when we're talking about the median here, these means are completely different because of this huge number at the end here. However, the median for both data sets, right? So if we look at 1, 2, 3, 4, 5, 6, 7, so n is going to equal 7 here, and it's the same as the bottom. So we know that the middle value is going to be the 4th value in, depth of 4, and we'll see that's 1614 and 1614. The median is still the same. So in both instances, it shows you how it's robust. It's resistant to the skews and outliers of a data set. This is also used in the housing market a lot. Normally in the housing market, you don't report the average price of a house in certain markets. Why? Because you have some houses that may be between probably majority houses are probably going to be between $100,000, $400,000 in a given type of market, but most are going to be between there. But there are some houses in some markets where there are $1 million homes, and these $1 million homes are completely far. They would basically almost consider outliers in some respects, and because of these outliers, it can really skew the data and reporting an average price that's not really accurate, where the median value is going to be the more accurate representation of the housing market, which is why if you ever go online and you look at houses, they'll report in the median value. The median value of houses sold this past month is whatever it is. They would never report on mean, because say only 5 houses were sold from a particular company, and one of them was $1 million home, and the other 4 were between $200,000 and $300,000. That $1 million home is really going to throw off the average price there because the sample size is very small. So they will always report the median value because that is going to be a more accurate representation of the housing market. Next we have mode, and I'm actually going to stop the video here so that way I have plenty of time to cover mode in the next video and going forward. So I will see you all in the next video.